But as I say, the units will not necessarily be mass. Okay, so thank you for bringing that up. I'll try to be more sensitive to that statement. So, of course, the reason for setting this up is that part of the, you say, why are you setting up this gigantic machinery with all of with the Lagrangians and so on? What in the world is the point of it? Well, the point of it in the end is not to do simple little F equal ma problems such as you did as an undergraduate and so on, but to set up and be able to do more complicated situations where, as you will soon see, and you do see in some of the problems, that life can be simpler, and in the end, that we can apply this to analogous situations, such as you will see later in quantum mechanics. But for example, the double pendulum is cited as one example, where you have a pendulum, a two-part pendulum, and it can swing, but it also can swing with a piece here, or indeed it could have many different links. And how to set that problem up to solve it nicely X and Y are clearly kind of clumsy coordinates for something that is moving like this. And so you want some better set of coordinates. So if you set this thing up in X and Y, it's going to be a bit messy. And it turns out that a better set of coordinates are this set of coordinates, which specifies the whole system with just, if I tell you those two numbers, you know where the pendulum bob at the end is explicitly with no ambiguity, right? So and then that's a nice system, and I didn't have to have
finding the
two sets of X's and Y's.
Sorry.
Yeah.
Finding the kinetic energy and the potential energy and setting up the Lagrangian, I think, is pretty doable. And then after that, to find the equation of motion, you just take the dr, or the partial L, partial r, and then the minus partial r L, partial r dot. I can't remember the exact equation. But and then the ddt of the first one.
Yeah.
Okay, and set that equal to 0.
So then we can play that game. Okay. So what else did I want to say from this? So we're going to get into talking about, so far we just talked about closed systems. We can talk about, you can see the way the game goes here. So we start out one particle and we say, well, we'll have a bunch of particles. And we'll say, this is a closed system. The next thing we'll say is, well, we have this closed system here, and we have another closed system over here. And these two maybe have an interaction between them. But if they're far away, then these guys over here won't know much about the individual locations over here. And I can replace, what we're getting around to, I can replace this cluster of particles by its center of mass and the interaction with this cluster as an ensemble. And so I can partition these, and then you can see how you induce to interacting with groups. And then we can talk about external fields. So one kind of external field, which is what the gradient of this U term gives you, is a constant force, which has some troubles, but it's a useful discussion to have a constant field. So if I put things in a constant field, like the constant gravitational field in this room, for example, which is Mr. G is the same all over here and pointing in the same direction. Or we talk about a constant electric field as between two big plates which are far away. If you start, as you know maybe from E&M, you start trying to integrate over such fields, eventually you get into trouble because the energy diverges. So you can't really have such things. But it's a good approximation for certain things. So we can consider a constant field. But in these terms, you're going to get into some trouble with conservation of energy. So often we'll talk about the conservation of energy within a system, an ensemble of particles, where it's perfectly well conserved. But if you're considering the external force field and coming from who knows where, a constant external force field that in which this whole ensemble is accelerated, then energy is not conserved within. Energy is conserved within the ensemble, but the whole ensemble is being accelerated. It's getting energy from somewhere. It's getting energy from that field. So in the giant sense, energy will be conserved, but you're going to have to put in whatever the source of that other field is. Or we can just ignore it. So just going from oh yes, right. And so there's a subtlety in I guess I can erase all this. If you guys do choose to look at and try to read the Landau book, let me warn you, you have to read very carefully, because Mr. Landau slips little things in that if you're not watching, you will get fooled. So I can take two systems where I have another system here, and I'll call this one A, and I'll call this one B. And I can write the total Lagrangian as being L equals T sub A, and no other forces around of QA and QA dot plus TB. Remember we talked about the additivity of these QB dot. And so it turns out then that we can write then for the Lagrangian for TA, for A, is equal to T sub A of Q sub A and Q dot A minus then this potential which comes from the effect of QA and QB of T. So this means that the effective potential energy, all this is saying is that the effective potential energy can be a function of time in this case. So for example, suppose that Mr. B here, think of it as being replaced by gravity, the gravity to this cluster of stars, and that this cluster is moving with time. And so the force over here is going to be a function of time. So we put that in that way. So we can wind up writing L is equal to 1s, we have said already, B squared minus U of R and T. And the equation of motion then, mv dot is equal to minus grad U of R. So, and indeed, in a uniform field, this then just goes to being U is equal to minus F dot R. So I know it seems like kind of a sleight of hand, but you get all the properties that you already have known since you were high school students or whatever of mechanics out of these few simplifying assumptions. And it seems like sleight of hand, but there they are. And as I was saying on the way in, this is the kind of thing that you would never start here in deducing the field. You only get there by already knowing how the whole game works and trying to write it down in this minimal fashion. Okay, so now we'll go ahead with, that was all in Mr. Landau chapter 1. We'll go ahead with what he does in chapter 2, which is derive a bunch of conservation laws. Oh, crap. I want to get through this today, so I don't know how far I'm going to get. Okay, so how many degrees of freedom do we have in a system of particles? Let there be S particles in the system, then we'll have two S functions. So we'll have 2S functions of the form of Qi is equal to Qi of T plus T0 and C1 through C2S minus 1. And the reason for that is that the time, I can always add, the time is relative. I can always add a constant to the time. And so I wind up with 2S minus 1 arbitrary constants. So you say, well, gosh, so what? Well, it turns out that a fair number of these, some of them are just where was everybody at t equals 0, but they can be rewritten in a different way to be various combinations, in particular constants of integration, which are therefore some quantity that is conserved, namely conservation of energy, momentum, and so on. So we can write down a bunch of these constants of integration. And so a general point that is made right away about that is that these constants of integration, whatever they are, all have the property of additivity. Another one of those sly little statements. And that is to say that I add up whatever these are over here, and I get a number. I add up the number over here, I get another number, and then I write down the equations for the whole bloody system, and I get a number which is the sum of these two numbers, except for the interactions of the two, which I may add another piece in. But if they're non-interacting, it is just the sum. Right. So here's from the homogeneity of time, and we can write down that dL dt is equal to sum of dL dqi qi dot plus sum dL dqi dot qi double dot. assuming that things are only a function of Qi and Qi dot. If there were some Qi double dot terms in there, then I'm going to have more trouble, right? So if L then had an explicit time dependence, then we would have a term in dl dt to be added on. But since there's not, then we can replace dl dq in accordance with Lagrange's equations. So this can then go to sigma qi dot d dt dl dqi dot plus sigma dl dqi dot qi double dot. I know a lot of this is really kind of mysterious. We seem to keep plugging the same equations in. We're playing this game with this differential. But then you see, therefore, that that is a total time derivative, so we can write that d dt of sigma qi dl dqi dot minus L is equal to 0, and therefore this is a conserved quantity, and we call this the energy. So you can write that the energy is equal to sigma q I dot dl dqi dot minus L. And so this is the conservation of energy equation. This is in this derivation, this is the definition of energy. You didn't have to call it the energy, you can call it whatever you bloody wanted. But see, it's defined in a very general. Write this Q sub I. What did I do something wrong? No. Yeah, minus L, and that comes from the homogeneity of time. Remember where this comes from. So that's all we really had to put in to get conservation of energy. So we're about to go back and do the next one, which is the homogeneity of space. We play the same game. Oh Christ! I'm too slow. From the homogeneity of space, here we need to, oh, this one's a little tricky. Here we need to do a little infinitesimal change in dl, sigma over a, dl dr sub a dot the is equal to this little vector epsilon dl dr sub a. Now, since epsilon is an arbitrary little displacement that we're applying to everybody if, or the equivalent delta L equals 0 implies that sigma A dL dRA is equal to 0, and then we play the game again with Lagrange's equations. We go sigma d dt dL dVA is equal to d dt sigma dL oh, yeah, right. Taking the t out front, VA is equal to 0, and therefore we have another conserved quantity, which, since this thing is 0, then we can define a new quantity, which just not surprisingly we call P dL dV sub A, and this is the definition of the momentum in the system when I take this sum over the A's. And so we can say that this quantity is constant for the system if it's not screwing around with some external system. Then that quantity will be conserved. The change with time is 0, it's a conserved quantity. Momentum is conserved, and momentum is conserved because of the homogeneity of space. You've heard that before, but that's a demonstration of it.
And epsilon is just some kind of small perturbation in space
Yeah.
that we use for proof, and then that's
Right,
it.
that's it. I don't care what it is. So, another sleight of hand, and all of a sudden, conservation of momentum pops out. And now, since we're essentially out of time, well, I guess I'm going to have to put off till next time, and I will go through this because it's just so beautiful. At the end, we go through a couple of things and talk about the homogeneity of the functions, the degree of homogeneity, and a whole bunch of things just come falling out, like Kepler's laws and so on.
Oh crap, wow. So you're going to finish the rest of chapter 2 on Landau?
I guess I better, yeah, because it's so nice. So, anyway, we have generalized forces from this sort of thing in the same way. And Landau makes the point, and I said it before, but let me say it again. In general, the PI are linear, homogeneous functions of the generalized velocities QI dot, and do not reduce to products of mass and velocity. They may be something much more ugly. But as long as they obey these relationships with each other, then everything's cool. Because you can remember, we can multiply the Lagrangian by anything we bloody want to, as long as we multiply all the Lagrangians by the same thing. Okay, so I think I better quit at that point.
Dr. Voss has us using
Chapter one.
Landau
Coaching.
for that man,
Okay.
so we're getting kind of
You're getting the last.
getting a whole terrible treatment.
Yeah, I don't think I ever looked at Landau.
No, I'll Google it.
I bet it's beautiful as well.
Chapter 1 is
Hopefully I have chapter 2 printed up by next time.
Well, yes.